Hi everyone. So we'll wait for another minute and then we can start. Okay, so before we start today's topic, just wanted to check. So I wanted to take the next class on this Thursday, that is 13th March. So when is a good time? Um, so I can see in your calendar that 13th you don't have class at 2 to 3:15, and then earlier in the morning. So which time is good? Anyone?
You can take it at two.
Sorry, 2.
Yeah.
Okay, fine. Um, and then after this Thursday, we'll have the next class on around 12th. Not around, but on the 12th. Sorry, not 12th. 22nd of March. That is next to next Saturday. Okay. So I hope all of you have submitted the quiz and the assignment, second assignment. Yeah. Yes. No.
Yes.
Any questions? Any questions? Any feedback on the assignment? Okay. So then I'll start. I think, did you have was there a conflict? Because I see today there are less students. Generally, it's around 10, 9 or 10 or 11. So I think you had some aptitude test right before this, right? Okay. Okay. So we'll first complete what we could not. Are all of you able to see my screen?
Yes, sir.
Okay. So we'll first complete what there was some internet network issue last time, 2 weeks back. So we couldn't complete a couple of slides here. So first we'll complete that. So the question. So this is in continuation of the topic of troubleshooting explainability issues. So the problem statement is, if I have different object if I have objective function values which are quite different, but the solves but the problem was solved to full optimality, then what could be the reason? So generally we think that uh, if I have two problems which have the same constraints but in different orders, they will have the same solution. It is not always so, or not always for every solver. So sometimes if the order of constraints or the order of variables in a constraint or the order of variables in the objective function vary, even that can cause then mathematically they're equivalent, but the solver would consider them as different. Consider them as different in the sense, the order of the sequence of pivoting, branching, etc. will be different. So we might end up with a different solutions. So in order to prevent, again, that is not desirable because it you will get different solutions every time you run the model, and that might confuse the user and even you, if you are doing some troubleshooting, or I mean if you're testing some new functionality on the result, then that might give you headaches. So in order to prevent this, most solvers have this concept of deterministic search and opportunistic search. So in deterministic search will take more time, because we are because of the number of threads we are using. But the guarantee is that your results, your search path and results would not differ from one run to the other, and the results would be repeatable across the different runs. That is, you'll be getting identical results across different runs. On the other hand, you can have opportunistic search. In opportunistic search, you will get you might get different results because the search path would be different, but this would also be faster than deterministic search. So it depends on your use case, whether you want a faster but non-repeatable solution, or you want a slower but rather repeatable solution. And another question is, you might ask, is why we would be getting different order of variables or constraints or objectives, variables and objective, if you're using the same code. So sometimes what might happen is, if you are running your code over a certain set of let's say products or machines, etc., and those products and machines are not sorted, then um, you might get different variations of the same equivalent problem. So ideally, whenever you are creating your set, I mean, after you have created the set, you should always sort it, so that you don't the problem that you are generating from the mathematical model is exactly the same in different runs. Okay, now moving to the next slide. Now another scenario is, let's say the objective function values are quite different as in the last slide, but and at the same time the problem was solved to a certain optimality gap, say 1%. That is, you are letting the model stop when you are just when you have achieved 99% optimality. So this might happen because in one solution we might be stopping at, and as you know, it will not exactly stop at 1%. It will stop at anything slightly beyond or equal to 1%. So in one run, it might stop at 0.95%, and in another run, it might stop at 0.9%, which are both less than one. But since the search path is different, the solution one, solution two could have different results if if you are using opportunistic search. Okay. Okay, and this is the four. Okay, this is the other slide. Are all of you still with me, or are able to see the screen? Able to hear me? You're all able to see the presentation, right?
Yes, sir.
Okay. So moving to the next slide. So this is another issue that, let's say in a factory, your demand is 10 units. The demand of a product is 10 units, and the capacity is 15 units, but the solver is able to allocate only 5 minutes, although we are minimizing the demand in the objective, sorry, minimizing unmet demand in the objective function. Now the user comes back to you and says that, hey, my capacity and demand are both greater than 5, but why is the model allocating only 5? So you can of course look at the problem, look at the LP file, look at the code, and try to intuitively solve the problem. But sometimes especially for complex networks, it is very difficult to solve the problem by intuition, unless the problem is something very simple. So you need to follow a systematic approach to root cause this issue. So the first thing that you would do is, you can put you want to ensure if X. So in this case, the user's question is, my demand is 10 and my capacity is 15, is greater than 10. So why is the model not able to allocate 10? So in order to check this, the first thing you will do is to ensure that there is no infeasibility between the problem would not become infeasible when, if this variable was allocated a value of 10, So let's say the variable is called x. So you will put an additional constraint in the LP file, x equal to 10, and resolve the problem. So the result that would be is, so what would happen after this is, if it is infeasible, if I mean, if x equal to 10 conflicts with any of the constraint, it would return, the model would return an infeasible result. But if it is not infeasible, then it will go ahead and happily solve the problem. So that's the first step. And now, if we if you if this if the model returns infeasibility, then as you have seen earlier, we can find out the constraint or constraints with which it is conflicting using IIS. Anyone remembers what is IIS? What is the full form of IIS? Anyone? Okay. So IIS is irreducible infeasible subset. So it is the smallest subset of constraints where if you remove even one constraint, the model would be feasible. So you can find out the reason of infeasibility using IIS if it is if it gives infeasibility. Now, if it is feasible but it worsens the overall objective function, then you can find out with which objective it is prioritizing over this one by looking at this table below. So if you look at this table below, then there are okay. So in this problem, there are three objectives: minimizing demand, minimizing unmet demand, minimizing cost, and minimizing the slack surplus with inventory targets. And the objective function values with x equal to 5 are 90, 150, and 30. And with x equal to 10, that I'm able to meet more demand because my objective function value reduces to objective function value for unmet demand reduces to 80 from 90, but my objective function value for cost and inventory target increases, and the overall increase is higher than the original solution of x equal to 5. In other words, it it worsens the overall objective function value. So in that means, that means now you can tell the user that, boss, if I mean, we can definitely allocate 10 units for X, but in that case, I would need to we would need to compromise on the objectives of, we would end up with a higher cost and inventory target, although my demand, and I'll be able to meet more demand, my cost and inventory target will increase. Now, the third thing that might happen is when you set x equal to 10 instead of when you set x equal to 10, it actually improves the overall objective function value. That means the model, you're getting a better result with x equal to 10 than with x equal to 5. So in that case, you can conclude that either there was a bug in the code, or the model did not convert to the optimal solution earlier because of the time limits or optimality gap limit that you had set. So that we will look at in the next slide. An extension of this problem can be a combination of points 2 and 3. That is, it might be a combination of both infeasibility and worsening objective function value. So if you increase x from 5 to up to 8, it will worsen the overall objective function value, but beyond 8, it will be infeasible. Now let's go back to point 4 in the next slide. That is if in case the overall objective function value improves with x equal to 10, what is the next thing that you would try or you would do? So now what you would do is, if there is some time limit or optimality gap limit, you will try to change that or remove that and see what is the result that you get after removing these limits. So that means you try to reach the globally optimal solution. So if the output still does not look good, then it might be that there is something wrong with the formulation. And if the output looks good but the time limit is too high, then we need to see how we can solve the problem within the time limit for x that we earlier had for x equal to 5. We will try to reformulate, or we'll try to apply some other techniques that we can get the same solution in, I'm sorry, you can get a better solution where x equal to 10 in the same amount of time. Okay. So I think this is all for this, what was remaining in this slide. Okay, so now let me go to the next slide, next topic. So in one of the early lectures, we had covered very briefly about commercial solvers. So I'll continue with that. So we had already gone through this. We had gone through this. Yeah. So for any commercial solver, there can be different types of licenses. So as you might be aware of, I didn't put on this slide, but you might have for academia, you would have academic license, which is free of cost, and you will also have some solvers. Okay, you'll have academic licenses free of cost, and when it comes to commercial versions, you might have different kinds of licenses. So one kind of license that you might have is developer license, which is installed locally on the OR developer's machine. So this is typically cheaper than an enterprise license because it is specific to a particular user. Um, and the second type of license is the server license, which will reside on the server or on the for the entire for all the computers of the enterprise, and any number of concurrent runs or any number of users is, there is no limit on the number of concurrent runs or the number of users who can use this simultaneously. And obviously this will be more expensive than the developer license. The third classification could be based on whether it is floating or non-floating, which means that if I once I get the, so floating, non-floating is okay. First, let me speak about floating. So, floating is once I get the key for the solver license, I can use it. I mean, whether X is using it or Y is using it or Z is using it doesn't matter. But the only constraint is at any point of time, only one of them can use it. But it is not specific to a single user. While in non-floating license, it is specific to a single user. So you need to provide you need to provide generally the host ID of your computer, which is specific to, it's like IP address. So it's specific to a particular laptop, particular machine, and the license would be activated only for that machine. So that is non-floating. And also these solvers allow trial versions. So let's say when you want to evaluate whether Gurobi can solve your problem, so instead of purchasing the license, you can use it for, let's say, 30 days free of cost, and see whether it is actually able to solve your problem. It is able to take care of your requirements, and if you're happy, you can go ahead and purchase the license for, let's say, 1 year. So that is called trial version. And the other point is some of these solvers have different functionalities or algorithms it uses. So, for example, like LP, MIP, nonlinear programming, quadratic optimization, and so on. So, depending on your, and the cost will increase with based on the number of, I mean, the cost that will be charged to you depends on the number of technologies or algorithms you want to buy the solvers for. So if you are only going for MIP, it will be cheaper. If you're going for MIP plus quadratic programming, it will be more expensive, and so on. So these are different types of licenses that a solver would have. And typically, whenever a company will purchase purchase any of these solvers, they need to purchase for 1 year, and it needs to be renewed after every 1 year. Okay. So now this is what a solver log looks like. That is the log after you run a model. So we had already gone through pre-solve in the earlier class. So pre-solve is the time taken to make any kind of logical reductions in the problem. And the next line is MIP emphasis. So balancing optimality and feasibility. So we'll come to this next few slides later. Here it specifies, it tells you the number of threads that it is using, one thread, and the amount of time taken for root relaxation is 0 seconds. And here below this, you will see the entire log of how the solver progressed towards solving the problem. So let's go through the different columns one by one. So nodes, so node is the number of nodes it has searched so far. Nodes left is the number of nodes remaining to search. Objective is the objective function value that we have reached so far. So given that in this case it is the objective function is decreasing, so this is a minimization problem. And the IL inf is the number of infeasibilities. Best integer is, so this being a mixed integer programming problem, this is the best integer value that you would get, the best bound. And in the last column you have the optimality gap, so how far we are from the optimal solution. So these are the different columns that we have in this log. And then these are the here it specifies the number of the type of cards it applies and the number of cards of each type. Solution pool, will come to solution pool later on. And at the end it tells you the status, so it's a MIP. So it's the integer optimal solution, and the objective function value is 3186. And it tells you the solution time, which was 0.01 seconds, the number of iterations it took, and the number of nodes iterations it required, the number of nodes explored, right? So after exploring 44 nodes and 131 iterations, this is objective function value obtained. And what else? Yeah, I think these are the basic things to look out for in the log. Okay. So okay, okay. So this is a description which we went through earlier. Okay. Okay. Now we'll see what are some of the parameters in commercial solvers. So in this lecture, what we'll see is we'll see how the mechanism of action of the solvers, some key features, and some some tips on how you can reduce the or improve the solver performance. One of them is One of them is parameter tuning. So parameters are different ways. I mean, parameters control the operation of solvers, and they typically operate the best at their default value. But in case you feel that for a particular problem that you have, a particular problem structure that you have, but a certain solver parameter needs to be changed, needs to be modified, then you can modify before the optimization begins. Another point is there are hundreds of these parameters, and obviously you cannot try one each of them one by one. And if you are changing multiple parameters, there can be again multiple combinations of parameter values, so you don't know which one would work best. Another point is this: the default parameter values that are used by the solver. This is obtained after this is decided, or yeah, this is decided by the solver after going through thousands of models from industry and academia. So it's very heavily tested. So only if you are completely sure that the parameter that you want to change to is would work better, only then you should change. And you should change these parameter values only if you see that it creates a big improvement across multiple test models. There is multiple data. So let's say without using the parameter, without making your parameter change, the solver takes 10 seconds, and after making or let's say it takes 2 minutes, and after changing it takes 2 minutes and 5 seconds, then probably it's advisable not to change solver parameter just for saving those 5 seconds, because that might create a bigger issue in some other data set. It might actually lead to a longer runtime in some other instance of the problem. Yeah, so why do we need so this is one area where academia industry connect is very useful or helpful. So in generally when in academia, the or when solvers also create their own data set, it will be randomly generated data. So it will not have the same it may not have the same properties as actual data, and you might see completely different behavior with actual data. So that's why it is very essential that solvers get access to the actual data as much as possible. And what happens is that whenever there are any unexpected results or performance issues in the solver, whichever company is using the solver, they will be sent. They can share the solver log or the LP file with the solver team, and then solver team will it might be it is expected to behave that way, or it might be that it is indeed a bug. So using that problem instance, they can they can fine tune the solver further. So that is a big win-win situation for both the company which runs into this kind of problem and the solver company. Okay, so now these are different types of parameters that exist in any commercial solver. So tolerances we have already seen in the last lecture. Then there are different parameters to control how simplex or barrier algorithms work. Scaling parameters, will come to that again. Different parameters for control the operation of MIP algorithms. Some parameters for pre-solve. Some parameters for so pre-solve, the parameters are, for example, if you want to turn off pre-solve, that is one parameter. Multiple solution will go through that later in the lecture today, and MIP cut. So again, we'll go through that later in the lecture today. In this one we went through yesterday. I mean, last lecture, this one also you went through. Okay. So now coming to MIP emphasis switch. So in optimization problem, as you know, the major objectives are finding feasible solution, finding optimal solution, and getting those feasible optimal solution as fast as possible. So the default approach of any solver would be to work rapidly towards an optimal solution, but in the beginning it will try to find high quality feasible solutions. But in certain cases, you might want to put more emphasis on finding more feasible solution. So in that case, you can go for this the second option. And the third option is you in some cases you may not bother at all about feasible solutions. You bother only about optimality. In that case, you can focus on optimality, which will in which case it will find feasible it will take less, it will spend less effort in finding feasible solutions early in the solve process. The other uh, other way in which it could work is by putting greater emphasis on proving optimality through moving the best bound values, so that detecting feasible solutions becomes almost coincidence. Hidden feasibility is finding high quality feasible solutions that are otherwise very difficult to find. So this is required when feasibility setting has difficulty in finding solutions of acceptable quality. And heuristic, there's one option called heuristic. So the objective here, so this is something which was recently introduced by Cplex. So this entirely focuses on finding high quality heuristic solutions as early as possible, and this almost puts no effort in moving the best bound and proving optimality. So this we should be considered when you don't care about optimality, or you know that you will never get an optimal solution, and yeah, other settings have difficulty finding solutions of acceptable quality. The next point is cut generation. So solvers will create some cuts on their own, so that it is it can reduce some of the non-feasible portions of the search space without removing any integer feasible solution. So now the question is whether is should we add more cuts or no. Again, this is not a very direct answer as always. So if you had add too many cuts, yeah, the formulation will be tighter, but it will also lead to slowing down of node processing due to more constraints in the node in the node LPs. So these two images shows the default cut strategy and the aggressive cut strategy. That aggressive cut strategy is when you decide to apply more cuts to your problem. So if you look at the default cut strategy on the left, then you would see that it reaches 38.64% optimal solution quite sorry, it reaches like around 41% optimal solution in 1 second, and then it is still stuck at 38% after another 3 seconds. um, on the other hand, in aggressive card strategy, we are able to reach um, 8% optimal solution in 34 seconds. Now, if you focus on this blue bar in both, I mean this blue rectangle in both the cases, you will see that in the default card strategy, we are not the number of cards we're adding or deleting is in hundreds, is in 3 digits, while in aggressive card strategy, it is in 4 digits. So what we observe from this two
Sir,
examples, yeah,
excuse me. Sir, can you tell us what is cut strategy?
I'm sorry, what is
Cut strategy.
card strategy? Yeah, yeah. Card strategy is that word and okay. So card strategy is how many cuts you will apply. Okay, so cut is basically constraints. So any constraint that you will be adding. Now you might be asking me that, so constraints I'm already adding in the formulation. I'm adding objective function, after that I'm adding constraints. So these are not user defined constraints or business problem defined constraints. So these are, so cuts, so these cuts what I'm talking about here, this addition, added, deleted, these cuts are essentially constraints which are added by the solver to reduce the search space and to increase and to reduce the runtime.
Oh,
So yeah, sorry.
no, nothing. Go.
Yeah, so by default, the solver will use a default cut strategy, but sometimes, like some solvers will have settings of 1, 2, 3. So one is like less. So default is default. You don't know what is the default. So default, the solver will decide the since it's default, the solver will decide the cut strategy based on the problem. But when if that particular solver has 1, 2, 3, that means one is less aggressive, two is medium, and three is more aggressive. So in one, it will reduce the number of cuts applied. Three, it will increase the number of cuts applied. Now, whether adding cuts will reduce runtime or not, that is not guaranteed. So that's what we are talking about.
Okay, sir.
Okay. Yeah, thanks. Yeah. So in this case, as you can see, by adding more cuts, we are improving the best bound, and the MIP gap decreases from 38% to 8%, right? But the time, we don't have the log after this, but it takes more time. So basically, the summary here is, if you need a good solution, a good meaning a feasible solution quickly, then adding more cards can be too expensive. But if you need a good an optimal solution, but you can afford to spend some time on it, then it might be better to add more cards. It might be better to add more cards. Whether the solver uses a default strategy or you add more cards by changing the default strategy, that's a different thing. But it might be beneficial to add cards. The other point here to note here is, so this is in terms of number of cards that you're adding. Another important point is how often cuts are created and added to a subproblem. So it's not that all these cuts are, as you're seeing here, these cuts are added at different points in time. So how often you add these cuts, that is also another important parameter. So you can again change that depending on your requirement. Now this is an example to show that it's not necessary that adding cuts will always be helpful. So if you see that if you have added a large number of cards to the root, but the objective function does not change significantly, then you can either turn off you can either turn off a particular type of cut or all the cuts completely. So this is the default cut strategy, picture on the left, and here you can see that it reaches the solution time was 4552 seconds, and in with all cuts disabled, the solution time reduced to around 3045 seconds. Okay. Yeah, so I think if you look at this log, you can relate to all the terms that we have discussed earlier. Heuristic still looking is something we have not gone through yet, so that is something we'll go through later. Yeah, apart from that, I think all the terms you are kind of familiar with. Okay. Um, okay, and these are the different types of card solvers apply, so I'll not go through this. You can read this up. Okay. Probably I'll come to this a bit later. Let me go to some other things here. Okay, so solvers have certain features which is aimed to make get solutions faster. So one is starting from a solution. So in simple words, what it means is if you know that you can already tell certain values of you can already pre-decide certain values of sorry, not certain values, you can pre-decide the values of certain variables, then you can fix that, and that will obviously reduce the solution space. So for example, going back to the sports match scheduling example assignment that all of you did, so you know that if two India Pakistan matches need to be played, they should be played on a Sunday evening, right? So you can set the that value, those corresponding variables to one. Now, you can so how do you know what is the so again the starting solution that has different we have different terms for that. We call it mid start or advanced start or warm start. So this can also come from previously solved problem with slightly with slightly different data. So for a particular problem, it's not that the data will change completely from one day to another day. So let's say if you have run a model for the next 6 months planning horizon, and again next month you want to refresh your run with revised input, so it's not that the results will change completely. So you can use the run. So you already have, so in this example you already have the previous results of the run from January to June. So January is anyways has crossed. So when you're running the model at the end of Jan, you still have the results of February to June from the earlier run, which was done a month back. So now you can use that as a starting point, and you'll of course not have the value for July, but you will have the value for the earlier values for February to June, and you can use that as a starting point for your next run. So this might reduce your model runtime because the solver has some idea about what value to start from, but it is not guaranteed. So we'll come to that. The other kind of knowledge you can have is based on on the business knowledge that you have. So in a vehicle routing problem, you know that at the end of the day, a vehicle needs to return to its depot. So ideally, it should again we are going back to, let's say, the ATM refilling exam problem that you all solved or are solving. So when the vehicle starts from the bank, from where it picks up cash, goes to the different ATMs, and at the end of the day it returns back to the bank probably, then it kind of probably a circular route would be helpful because it needs to return to the same location. So if we can use that knowledge and provide some initial starting value. Also, you can determine a feasible solution manually, meaning using some heuristics and feed that into the model. Also, you can use a suboptimal solution. You can put an optimality gap of very high, like let's say 30% away from the optimal solution, which you'll get for which you'll get a solution quite fast. and you can use that as a starting point and feed that into the model to get a much better solution. Also, you can provide multiple MIP starts and let the model decide whichever is the best one out of this, which will be best in the sense which will lead me to the best objective function value. And the MIP start may not always be even a feasible solution. It can be an infeasible solution, or it can be an incomplete solution of the model. Incomplete meaning which has not run till optimality, full optimality. So it can be of any type. So let's say if you're feeding an infeasible solution, the first thing the MIP will try to do is the solver will try to do is try to bring it make it feasible, and then we'll try to improve the optimality. Yeah, so this is some theory. Okay, now the question is starting from warm start solution always guaranteed to improve solver performance? No. So in this case, we are gambling that the time spent in computing the initial solution will be offset by would be not required. But what you might have done in the process of providing a warm start is you might have altered some of the cuts the solver generates, or you might have removed the less productive. You might have added some less productive portions of the search space, so that might actually worsen your solver performance. So if you see that without the warm start your solver is performing better, then probably it's not worth warm starting. And this could happen if the solver's heuristics or solver's internal logic is better than yours, or just your bad luck. Yeah, I think this point I'll skip. Okay, so all of you know about heuristics, any kind of logic that you apply to solve problems, even in optimization. We use instead of using optimization model, we use heuristics, especially to solve very complex problems like VRPs. So internally, also the solvers apply some heuristics, which produce good and approximate solutions to a problem, but lacks theoretical guarantee. And they may produce multiple solutions which satisfies all constraints and integrity conditions, but we are not sure if that is the globally optimal solution. So the main concept behind heuristics logic is to get some quick dirty solutions. Now there are different kinds of heuristics to find. There are different kinds of heuristics which simplex any solvers apply. So we'll not. So these are the different kinds of heuristics, but I'll not go through in details. But again, like cuts, even in heuristics, there is a parameter by which will determine how frequently you need to apply the heuristics, which is again modifiable by you. Okay, so I skip this. I think we have already gone through this. So I think this is one slide we didn't go through in the last lecture. So okay, so instead of me answering the question, so let's say if you're, so all of you remember what is pre-solve? Anyone can tell me what is pre-solve? Anyone? So if you if you see that pre-solve is removing all the rows and columns in a problem, it does not mean that your formulation is wrong or your input data is wrong or solver is doing something. Solver is messing up with something. It just means that the problem is a bit trivial. That is why just by logically reducing all the constraints and tightening the bounds, removing the variables, etc., it is able to solve the problem. Okay, and there is another logic called probing, which is used by solvers, and this is specific to problems which have a lot of binary variables. So in binary variables, as you know, can take only the value 0 to 1. So what probing does is it will fix the value. So let's say in your problem you have 1,000 binary variables, so it will take up any particular variable fix the value to either 0 or 1, and it will so let's say it fixes the value of particular variable to 0, and then it will see the, since that variable will be there in multiple constraints where you have other variables, so it will see the impact on the other constraints, and it will see if setting that variable equal to 0 made anything infeasible. So if it makes anything infeasible, then 0 is not the possible solution. It should be 1. So it will set the value of that variable to 1. Similarly, it will repeat this process for all the binary variables. So the amount, again, obviously you can as you can understand, this will take a lot of constraints. So this is, it can be sometimes beneficial because you are fixing the values. You might be able to fix the values. The time required for probing would be high, but
Sir,
if it is
excuse me,
it
sir.
might be offset by the time that is saved in
Hello, sir. Hello.
computing the value of
Hello,
those variables later, because we already know the
sir.
values of those binary variables from probing. So how much probing you want, that you can change, you can configure. So by default, solvers will
So
apply the
your
default
voice is
probing, and you
breaking.
can Mhm. Yeah, yeah.
Your voice is breaking.
Is it is it better now?
Yes, sir.
Okay, okay. So I've stopped my video. So yeah, you had a question. You wanted to say something?
No, no, no. About this voice, I
Okay,
interrupted
okay.
you.
So you are there with me till probing.
Yeah,
Okay. Okay. Yeah. So basically, by using this probing, then we can reduce the number of binary variables that the actual optimization model needs to solve. Um, yeah, I think that's it about this slide. Now, these are different scenarios that you might find in any problem. So the one is so the first the one scenario is when the model takes when the solver takes some time to get the first feasible solution. So it could be due to slow root relaxation or slow node progress or no feasible solution found. So in the third so let me first go to the third example. The third example, as you see, the objective incumbent column is empty. So it has already progressed for almost 2,600 seconds, but nothing has been found yet. Similarly, in the other two instances. And okay, in this instance, as you see the gap, we have already made progress for around almost 29,000 seconds, but the optimality gap is still 100%. Okay. So if there is lack of movement in the best node, then you could try any of this probing, strong branching. We have not seen what is strong branching. We'll come to that. And setting MIP emphasis to 3, that is, you put emphasis on moving the best bound. Okay. This is all fine. And if you're not able to find more feasible solutions, you can either you can try changing any of these parameters. Similarly, too much. Okay, I'll come to this. Okay, first I'll come to this one. Okay. Okay, so now we have something called solution pools. Solution pool is essentially, just give me a second. Solution pool, an example is in Google Maps. You have seen that whenever you try to enter, you enter a particular destination, a particular point as your destination location. Sometimes it will show you multiple routes with the total, with the kilometers and the time required, and then it's up to you to decide which is best. And it will not show you routes which are like very long. So in this example, the routes are between 36 34 to 37 miles, so it has a deviation of around 2 miles between the maximum and minimum route. And in terms of time, the deviation is 6 minutes. So it will show you routes which are kind of close by. But again, there might be a route which is like this, which is like instead of which is like, let's say, 50 kilometers. So obviously it will not show you that right route. So now once it shows you the three primary routes, you are free to decide which one you want to go for depending on your requirement. So the same thing happens in optimization, that sometimes uh, either we want to store multiple solutions, or the user wants us to store multiple solutions for the same model. So the first, if we are storing, so for example, three solutions, then the first solution would be the globally optimal solution, and the next two solutions would be a bit inferior to the worse than the globally optimal solution. And the reason why we need to do this sometimes is that certain requirements, some objectives, or some constraints are sometimes a bit difficult to formulate efficiently as linear expressions, or even to quantify in exact terms with exact coefficients. So in such cases, if you are able to provide multiple solutions, then based on the user's requirement, they can decide which one would suit them the best. It is also helpful when you are demonstrating the power of optimization. So instead of showing just the optimal, globally optimal solution, you show some solutions which are a bit worse, less in value, but then the user can easily understand that why the globally optimal is indeed the globally optimal solution. um, so this kind of solution pool helps the user to accept a suboptimal solution which is better according to some criteria, but is not captured by the model design. So the model should ideally incorporate those that unspecified criteria, but sometimes it is difficult to do that. So how do you, what can be the different types of alternative solutions? So one metric could be solutions which are within a given percentage of the optimal solution, globally optimal solution. So let's say within 5% of the globally optimal solutions. The other option could be, other variety could be a set of diverse solutions. So in the map example, map picture shown here, in that case, a diverse solution could be, one solution could be, for example, a road which passes only through national highways. The second solution could be a road which passes through, through areas which are not in the main road. So based on your requirement, you can choose. So for example, if you want to go through, or the third option can be, it can show you some scenic route. So based on your requirement, so if you want to reach the destination a bit faster, like let's say 10 minutes faster, you can take the national highway. If you want to go through a locality, so that you can stop at a restaurant, you can have breakfast or lunch, then you can take that option. Or if you want to follow the scenic route, even if that takes you 10 minutes more, you want to take scenic route, that is the third option. So these are the different types of diverse options that you can have. The third option is collect solutions with specific properties, for example, filtering solutions based on their validity in an additional linear constraint. The fourth last solution could be collecting all possible solutions to a MIP model which are within a certain threshold. So now the question that I have for you is the solution pool same as, so all of you would remember multiple optimal solution or alternate optimal solution earlier. So is solution pool same as that, or is it different? Anyone?
So in solution pool, solution need not be optimal, right?
Mm-hmm.
Yeah. So in that way, it can be different.
Okay, yeah, it's different. So alternate optimal solution means the objective function values are same for all the solutions, but in solution pool that is not required. Okay, so sorry, where was I? Yeah. Now moving back to the next slide, moving to the next slide. So this slide shows how much solvers have progressed in the last whatever 20-30 years in terms of algorithm improvements, new techniques to embedded to reduce runtime. So this screenshot is of, I guess, of Cplex. So it shows the versions, which what was the release date, etc. And it is estimated that MIPS alone got faster by 22% every year during the last 20 years, purely from algorithmic side. And this, so purely from algorithmic side, anyone can explain what is the meaning of that? I mean, what can be the other improvement apart from algorithms in this context? Anyone?
Like
Okay.
hardware improvement.
Right. So computers have increased. So as you have seen, these MIP problems are very memory intensive. So in the last 20 years, there has been enormous development in the hardware storage. I mean, not storage, but processing capabilities also, CPU capabilities also. So that has also increased. I mean, that has an additional impact on solve time. So yeah, so that is the other point. And so what used to take hours earlier, like 25, 20 years or 30 years back, the problems which used to take hours earlier, so those could now be solved in in seconds, and problems which were unsolvable earlier due to the sheer due to the sheer size and complexity, those you can solve in hours now. So that is the impact. And so what we do in any organization is, when we are going for commercial solvers, we try to upgrade the solver version every year, because obviously this when once you purchase the solver, once you purchase the commercial solver, you are absolutely open, free to I mean, you can freely download the upgrade to the latest version. But again, when you upgrade, it's not just a blind upgrade, so you need to check for certain things. So if you are using, for example, Python with your solver, then you should ensure that the latest version, I mean the version of solver that you're upgrading to, is compatible with the Python version also that you are using. Otherwise it will fail. And let's say in your on the server, if you have multiple models optimization, I mean multiple models in the sense of models for multiple projects. So let's say you are working on one project, I'm working on another project, etc. So there are like 10 different models. So when you change the solver version, it will be applicable for all the projects, not just your project. So that's something you need to be careful about. And so you should make sure that the latest version is compatible for all the models. And also we should check which version is safe to upgrade to, meaning sometimes the latest version is not the most it might have more changes, it might be a little more faster than just the previous version, but it may not be safest to upgrade to the latest version, because it's not that it has not that been heavily tested by all the users. So in other organizations, so it might be safe to upgrade to a version which is more stable, which was released maybe, let's say, 2-3 months back. So those are some of the rules we should keep in mind. Okay, I see we have only two people now, so I think Utpal mentioned that he had a class at 5. So shall we stop now and continue in the next lecture, or you want to continue?
Sure, sir.
Okay. 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 So fine. So next class we'll have on Thursday. 2 to 3:15. Okay, and we'll 2 to 3:15, right? Thursday. Okay, so and I'll try to make it a bit longer so that we can compensate for what we the minutes 15 minutes that we did not do today. So we'll have like 2 to 3:30 on Thursday then.
Okay, sir.
Okay. Okay. Thanks. Thanks, man.
Thank
Thanks,
you.
Rachel.